I really should not have looked this up. Number 10. Unusual lunar colors. The crew called it out live. From the Orion window, parts of the moon looked green and brown, not the flat gray you learned about in school. When trained astronauts report that the surface looks colorful, the entire scientific community stops and pays attention. Here is what is actually happening. Small changes in the mineral mix across the surface cause subtle but very distinct color shifts. Iron-bearing minerals and titanium-rich patches reflect sunlight differently. The harsh, unfiltered angle of the sun exaggerates those differences further. A human eye staring through a capsule window catches what orbiting cameras sometimes miss entirely. Scientists on the ground cross-checked the crew reports against orbital spectra and decades of lunar data. Some patches reflect iron-rich volcanic glass, while others show titanium-heavy rock that looks nearly black until the sun hits it at just the right angle. Of course, photographers online pushed up the contrast, and suddenly a subtle scientific clue turned into a full-blown internet headline. That distortion actually matters because policy decisions and engineering budgets respond to headlines, not footnotes buried in research papers. If those unexpected hues mark different and potentially reactive chemistry, then the landing zones we mapped for future missions might be sitting on top of serious dangers we never anticipated. The machines we send to dig will need entirely different drill bits. The filters we rely on to process breathable air will need to handle a wider range of soil compositions than anyone originally designed for. Resource processing systems built for uniform gray dust might clog or fail completely when they encounter something chemically hostile. The safe approach is brutally simple. Treat every colorful patch as a potential hazard and test it on site before committing heavy hardware. Send landers that can sample the actual soil, not just cameras that take pretty pictures. Design drills and filtration systems for a range of soil types. Plan redundancy into everything, because the moon is already screaming at us that it is far more complicated than our old maps ever suggested, and color is simply the first warning. Number 9. Meteor impact flashes. Imagine staring out into pure darkness from a capsule window as you orbit the far side of the moon during a nearly hour-long eclipse. Suddenly, out of the black, 6 distinct flashes of light pop off across the surface, like flashbulbs going off at a press conference. Those were not camera glitches, they were meteor impact flashes, confirmed by ground telescopes and mission telemetry, without an atmosphere to slow them down or burn them up. Tiny rocks from deep space slam into the lunar surface at speeds exceeding 45,000 miles per hour. They strike hard enough to vaporize on contact and explode in pure light. Scientists in mission control cheered when they saw the data. But that excitement hides a genuinely terrifying reality. On the moon, a micrometeoroid that would burn up harmlessly in our sky hits like a high-caliber bullet. A single lucky strike on a rover's radiator could disable cooling and kill the machine. A punctured habitat wall could trigger explosive decompression. A crack in an astronaut's helmet visor is a death sentence measured in seconds. Engineers can add shielding, but protection adds mass. Every extra kilogram of armor means another launch cost, another delay, another budget fight in Congress. So engineering teams are thinking in layers now. Bury habitats under thick blankets of regolith to absorb kinetic energy. Build hard outer shells using multiple thin layers specifically designed to shatter and scatter incoming fragments before they punch through. Place sensitive electronics and life support inside recessed bays where flying debris cannot reach. Add full redundancy to power and breathing systems so that a single puncture does not cascade into total catastrophic failure. Monitor the sky around the clock with orbiting impact detectors and simple ground sensors. And most critically, choose landing sites in regions where impact flash frequency has been historically lowest. None of this is cheap. None of it is easy. The encouraging part of Artemis is that we can now map the danger before people move in permanently. The disturbing part is equally clear. Until we can reliably predict exactly where the moon gets pelted the hardest, every lunar base will exist under an invisible, relentless rain of cosmic bullets. Number 8. Potential water ice in lunar craters. It is the holy grail of everything we want to do off-Earth. Astronauts and instruments both pointed to unusually bright patches inside the permanently shadowed craters near the moon's south pole. These hollows have not seen a single photon of sunlight in billions of years. On Earth, ice surviving in those conditions would be impossible. On the moon, it is exactly where frozen water can persist across geological time. Radar echoes, thermal readings, and direct visual reports from the Artemis crew all converge on the same conclusion. Something frozen is hiding down there. Why does that matter? Because off-Earth, water is not just for drinking. It can be split into oxygen for breathing and hydrogen for rocket fuel. It can sustain pressurized greenhouses and keep critical electronics cooled. A reliable water source on the moon would change the economics of space exploration permanently. That sounds like salvation until you hear the catch. Most of these deposits are not clean, pure ice sitting in convenient pools. They are hopelessly mixed with jagged regolith and rock. Some may be impossibly thin slabs buried under a thick crust of lunar soil. Others might be nothing more than scattered frozen grains locked into a concrete-like matrix that requires enormous energy to break apart. Robotic prospectors will go first. Landers will carry drills and microwave probes to test exactly how ice is entangled with the surrounding material. Some extraction methods use focused heat to sublimate ice directly and then capture the vapor as it rises. Others physically scoop the frozen soil and melt it inside sealed processing chambers. Every single approach demands significant power, and power is the one thing you cannot easily get at the bottom of a crater where the sun literally never shines. There is also a chemistry problem nobody talks about publicly. Lunar soil can contain volatile compounds that react aggressively with processing hardware or clog filtration systems. That means extraction is not just a digging problem. It is a chemistry and engineering puzzle performed under extreme cold in permanent darkness. If we design billion-dollar missions assuming easy access to water, and that water turns out to be unreachable or contaminated, an entire lunar outpost faces a supply crisis with no rescue coming. The moon is offering us an extraordinary promise, but the price of claiming it may be far higher than anyone has publicly acknowledged. Number 7. Snowy crater textures. The astronauts describe some craters as looking dusted in white, as if someone had carefully sprinkled powdered sugar across the rocky landscape. It is a beautiful mental image, but it is dangerously misleading. The moon has no weather, no snow, no frost cycles. So what are those strange ghostly patches that shine back at the observer like fresh powder on a ski slope? The leading scientific explanation is actually straightforward. Fresh, small impacts blow out lighter material from underneath the darker surface crust, exposing pristine subsurface regolith that has never been darkened by space weathering. Another cause is volatile deposits that slowly accumulate in regions where direct sunlight never penetrates. Extremely fine particle size and microshadows between individual grains make these spots reflect light far more intensely than the surrounding terrain. The practical danger is immediate and real. A landing team expecting firm, solid ground might set down on a soft, powdery pocket that swallows a landing leg or an astronaut's boot without any warning. Drills designed for packed regolith could jam instantly in the fluff. Anchoring systems meant to secure habitat modules might simply pull out of the ground under the slightest load. Power and thermal systems calibrated for dense soil will behave completely differently when sitting on top of highly reflective, loosely packed material that insulates heat in unpredictable ways. Engineers must now treat every bright patch as actively hostile terrain until a robot physically tests it. Small robotic scouts will carry penetrometers, instruments that push a metal rod into the ground and record exactly how much resistance they encounter at each depth. If the rod sinks fast, the surface is dangerously loose and unstable. If it holds firm, heavier hardware can follow with some confidence. Thermal probes will also need to measure how these bright zones behave when a rover's shadow falls across them, because fluffy regolith traps and releases heat in patterns that can overheat wheels, tracks, and delicate instruments. Sample return from these patches will reveal whether volatile compounds are sitting just below the surface, waiting to react. That chemistry determines whether a given zone is merely dusty or chemically aggressive. Until those answers physically come back from the moon, every bright crater floor remains a question mark that could swallow equipment, corrupt samples, or cost human lives. Number 6. The giant bullseye basin. Artemis II carried humans farther from Earth than anyone in all of recorded history, and for the first time allowed modern eyes to sweep the entire far side of the moon in a single, unbroken pass. From the capsule window, the crew watched a colossal bullseye of concentric rings and ridges unfold below them, a basin stretching across a region roughly the size of a small continent. Seeing that structure all at once is fundamentally different from assembling flat photographs on a screen. It gives you visceral, immediate context. It reveals exactly how ancient, catastrophic impacts tossed debris across thousands of kilometers and how lava flows and deep fractures stitched the surface into a fractured patchwork of hidden geological hazards. That perspective matters because it shatters assumptions about safe ground. Zones that looked perfectly smooth on older, low-resolution orbital maps actually contain deep layering, unexpected steep slopes, and concealed ejecta blankets that could behave like unstable talus on a mountainside. For mission planners, That means landing sites chosen decades ago, using grainy photographs, may actually be sitting on top of fractured ring structures or hidden debris fields that will collapse under the weight of a lander. There is another dimension that makes the far side uniquely dangerous. You cannot land there and maintain a constant communication link to Earth. The moon's own bulk blocks every signal. Any far side base will need dedicated relay satellites or a local communication hub, and each of those adds mass, complexity, and entirely new failure modes. Sample return missions become trickier because every additional relay satellite is another thing to build, launch, protect from micrometeoroids, and keep operational for years. Scientists gain something enormous in return, however. The basin rings and overlapping ejecta blankets preserve a layered timeline of impacts and early solar system violence that simply cannot be read from the near side. Those geological layers could answer fundamental questions about how water and heavy elements originally arrived at the moon and whether similar delivery mechanisms seeded the early Earth. For engineers, the conclusion is blunt. Site selection must evolve from low-resolution orbital photography to boots-on-the-ground reconnaissance by robotic scouts. Those scouts must map slope stability, identify hidden boulder fields, and test soil-bearing capacity before any human crew sets foot on the far side. The far side of the moon is no longer just a mysterious dark hemisphere. It is a logistical and survival puzzle that will demand an extraordinary investment of time, money, and hardware to solve. Number 5. Deep space radiation. When Artemis II pushed beyond the protective cocoon of Earth's magnetic field, it reminded every mission planner of an invisible, relentless truth. Deep space is saturated with particles that chew through metal and human tissue without mercy. Sensors inside the Orion capsule prove that while shielding works, it does not work evenly. Where you physically sit inside the cabin changes how much radiation your body absorbs. That is a massive problem because radiation damage is completely cumulative. It never resets, it never heals, it just builds. A single severe solar storm can spike exposure levels in minutes, delivering a dangerous dose before anyone fully registers the alarm. Meanwhile, a constant background hum of galactic cosmic rays slowly damages cell DNA, disrupts neural tissue, and silently corrupts computer memory over weeks and months. The effects are straightforward to list. Electronics randomly malfunction. Stored mission data gets corrupted without any visible cause. Human tissue accumulates mutations, and over time, that steadily raises the probability of cancer, cataracts, cardiovascular issues, and cognitive decline. Engineers have a toolkit, but every solution comes with a painful trade-off. Add thick shielding material around critical habitat zones, and you protect people, but you also add enormous launch mass and cost. Build compact internal storm shelters where crew can retreat during peak solar events, but that means sacrificing living space. Bury sensitive computers deep inside layered structures designed to fragment incoming particles, but that increases maintenance complexity. Use real-time solar observatory data and onboard particle detectors to give crews early warning. But those systems themselves need to survive the radiation they are monitoring. New technology is helping. Tiny biological organ-on-a-chip sensors can now detect subtle tissue damage before clinical symptoms appear. Engineers are also experimenting with radiation-tolerant processor architectures and redundant computing setups where one corrupted system gets instantly overridden by backup hardware. All of these measures work together, but none of them erase the fundamental biological limit. The longer any human stays in deep space, the more cumulative risk they accept with every passing hour. That means mission duration must be balanced against a very honest exposure clock. Until we can dramatically extend that clock through better shielding, better medical countermeasures, or both, the dream of humans living on the moon for years at a time is not just ambitious. It is a medical experiment with real people's bodies on the line. Number 4. Mysterious surface squiggles. The Artemis crew reported strange winding features across parts of the lunar surface that looked exactly like someone had dragged a giant finger through wet sand. Scientists nicknamed them squiggles because they do not match any known lava channel formation, standard impact ray pattern, or recognized geological process. The features are genuinely puzzling, and the leading explanations are deeply unsettling for anyone planning to put hardware or people on the surface. One theory is electrostatic dust transport. Ultraviolet light and solar wind constantly bombard the lunar surface, stripping electrons from exposed dust grains and giving them an electrical charge. Those charged particles can then hop and levitate above the ground under the right conditions. Laboratory experiments at the University of Colorado demonstrated that simulated lunar dust grains are capable of lofting themselves up to a full meter above the surface. Over thousands of years, this slow, invisible migration could pile charged dust grains into those winding tracks that are plainly visible from orbit. Another explanation is shallow tectonic creep. As the moon's interior cools and the whole body contracts, the crust shifts just enough to cut tiny faults that naturally channel loose debris into curving lines, like drainage patterns forming in a dry riverbed. A third possibility involves the remnants of ancient lava tubes that partially collapsed eons ago, leaving behind snaking surface depressions that accumulated wind-blown dust over geological time. The real answer may be all three processes acting simultaneously in different regions at different times. Why does any of this matter for the people building lunar hardware? Because if electrostatic forces are actively moving dust across the moon's surface right now, today, then every single piece of equipment we place there faces a slow, invisible siege. Fine grains will work their way into mechanical joints and slowly grind them into non-functional metal scraps. They will coat solar panels layer by layer, steadily dropping power output until systems start failing. They will penetrate supposedly airtight seals and contaminate the breathing air inside pressurized habitats. Apollo astronauts reported decades ago that lunar dust clung aggressively to everything they touched and irritated their lungs within hours of surface exposure. Magnetometer readings from orbit now suggest that some of these squiggly regions sit directly above patches of remnant crustal magnetism, which may focus charged particle flow and intensify dust lofting in those specific areas. If those squiggles are actively growing or shifting in the present day, the moon is quietly rewriting its own surface beneath our feet, and our equipment is already losing the fight. Number 3. Silent moonquakes. Imagine standing on a surface that everyone has confidently told you has been geologically dead for billions of years. Then the ground beneath your boots starts to tremble. The moon is shrinking. As its incredibly hot interior slowly cools over geological time, the entire body is physically contracting. That contraction forces the brittle outer crust to crack and buckle under enormous compressive stress, forming cliff-like ridges called lobate scarps that scar the landscape. In February of this year, researchers published the first truly comprehensive global survey and discovered over 2,600 of these active fault ridges scattered across the lunar surface. Over 1,100 of them had never been cataloged before by any previous mission or satellite survey. Each ridge marks a fault, and many of those faults are disturbingly young in geological terms, meaning they formed within just the last few 100 million years. In lunar geology, that is practically yesterday. Apollo-era seismometers recorded shallow moonquakes reaching magnitudes of 5, that is significant on any planet. But here is the detail that genuinely frightens the people designing lunar habitats. On Earth, a magnitude 5.0 earthquake shakes the ground for seconds, maybe a minute at most, and then it fades. On the moon, because the dry shattered rock has almost zero natural dampening capacity, a single moonquake can rumble continuously for hours. The vibrations have nowhere to go. They just bounce around inside the crust, recycling and amplifying, refusing to die out. For a lunar base, prolonged shaking changes every engineering calculation. A habitat structure designed for static loads could develop dangerous fatigue cracks in its walls, joints, and pressure seals after enduring hours of relentless vibration. Regolith carefully piled on top of modules for radiation protection could shift and avalanche during a sustained event, ripping away the shielding and exposing the fragile shell to cosmic ray bombardment. Boulders perched on nearby slopes and ridges could shake loose and roll directly into solar arrays, communication dishes, or crew modules with devastating force. Scientists have already matched visible boulder tracks in high-resolution lunar reconnaissance orbiter photographs to nearby lobate scarps, providing strong physical evidence that past moonquakes shook those massive rocks free. Landing sites near the South Pole, which is where Artemis III plans to put boots on the ground, are now being actively screened for proximity to recently active faults. Future missions are planning to deploy the Lunar Environment Monitoring Station, known as LEMS, as a permanent seismic listening post on the surface. Until that long-term data arrives, mission planners have no choice but to treat every potential site as seismically active. We called the moon a dead rock for 60 consecutive years. That was completely wrong. It is slowly and silently cracking apart, and any base we construct there will absolutely feel it. Number 2. Solar eclipse anomalies. On April 6th, the Artemis II crew drifted through the moon's vast shadow and experienced something no human being in history has ever witnessed. A total solar eclipse lasting 54 uninterrupted minutes. On Earth, the most spectacular total eclipses give you maybe 2 or 3 breathtaking minutes of totality before the sun reappears. The Artemis crew had nearly an hour to observe the sun's outer atmosphere, with zero atmospheric distortion, zero light pollution, and zero obstruction. What they recorded unsettled solar physicists around the world. The corona, the massive glowing halo of superheated plasma that surrounds our star, appeared far more extended than any existing mathematical model had predicted. Specifically, researchers published a peer-reviewed analysis in the astrophysical journal Letters showing that the optical F corona, which is sunlight scattering off interplanetary dust, stretched significantly further in the north-south direction than any simulation or ground-based observation had ever suggested. That single finding means our maps of dust density in the inner solar system need a fundamental revision. During the extended totality, the crew also documented Earthshine reflecting off the darkened lunar surface and clearly observed Venus and deep-field background stars that are normally completely invisible when you are this close to the Sun. These bonus observations are scientifically valuable on their own, but it is the corona anomaly that has the most dangerous implications. Why is a surprisingly extended corona genuinely frightening for future missions? Because the corona is the birthplace of space weather. It is where coronal mass ejections form and where high-energy particle bursts originate. These events are the single greatest acute danger to astronauts working beyond Earth's protective magnetic field. If the corona's actual physical structure and reach differ from the models we have relied on for decades, then our predictions of when solar storms will arrive and how hard they will hit are fundamentally flawed. A solar storm arriving faster or spreading wider than forecast gives astronauts critically less time to reach a radiation storm shelter. Radiation levels inside a habitat could spike past emergency thresholds before anyone processes the warning. Electronics could suffer permanent damage without any advance indication. Communication links to Earth could drop at the worst possible moment, leaving a crew completely isolated during a medical emergency. The extended F corona data also implies there is more interplanetary dust floating between the planets than we accounted for, which increases the rate of micro-impacts on spacecraft hulls, optical instruments, and solar panel surfaces across long-duration missions. The Sun looked serene and beautiful during those 54 minutes of totality. But the data brought home by the Artemis crew tells a very different story. Our local star is significantly more volatile and unpredictable than we assumed, and our existing warning infrastructure may not be fast enough when it decides to violently erupt. Number 1. The Moon's unknown chemistry. After everything else on this list, this final discovery might be the most quietly terrifying of all. We do not fully understand the chemical composition of the ground we are planning to build on, drill into, process, and breathe filtered air through. The color data from Artemis II, combined with years of orbital spectral analysis, hints at a reality that no mission planner enjoys confronting. The Moon may be harboring volatile compounds, bizarre mineral combinations, and possibly trace organic molecules that nobody expected to find there. We still do not fully know where the Moon's water originally came from. We do not know why some regions contain dramatically higher concentrations of volatile chemicals than others. We do not know how deep those puzzling color patches penetrate below the surface. These are not abstract academic curiosities. They are fundamental unknowns that change what kind of world the Moon actually is, and how it will respond when we start aggressively disturbing it. If water was delivered to the Moon by comets over billions of years, then ice deposits may be extremely localized and rare, clustered in random, unpredictable pockets. If water is somehow native to the lunar interior, tied to hot geological processes deep below the crust, then it could be far more widespread. That single distinction determines whether a permanent base can survive on local resources, or whether it must be continuously resupplied from Earth at staggering cost per kilogram. Then there is the chemistry of the dust itself, and this is where it gets genuinely frightening. If the regolith contains reactive compounds, highly oxidizing minerals, or unexpected perchlorates, it could corrode metal landing gear on contact. It could eat through the flexible joints of EVA suits during routine surface walks. It could destroy air filtration membranes and water purification systems within days of first exposure. Apollo astronauts already described the smell of lunar dust as something like spent gunpowder, a sharp chemical odor that suggests aggressive reactivity. If there are also unexpected organic compounds in the soil, the scientific payoff would be enormous, but it would simultaneously force us to ask deeply uncomfortable questions about how those organics got there in the first place. Scientists can begin answering these questions with targeted lander missions and returned sample analyses, but every sample return takes years of planning and costs billions of dollars. In the meantime, mission architects must assume the worst-case chemistry and build enormous safety margins into every system that contacts the lunar surface. Every drill, every filter, every seal, every square centimeter of suit fabric that touches regolith must be designed to survive contact with something potentially corrosive and toxic. The final haunting truth is this: every answer we bring back from the moon will raise 10 more questions we never thought to ask. The moon is not a solved backyard waiting to be colonized. It is a complex, chemically active, seismically restless, and deeply mysterious world that will generously reward patience and will brutally, unforgivingly punish any species arrogant enough to underestimate it. After 60 years of calling it a dead gray rock, we are only now beginning to understand how wrong we were. The real question is whether we have the humility to let the moon teach us before we commit to living there permanently.